Hello everybody and welcome to a review for Calculus 4. This is going to hopefully help you get ready to take a multivariable calculus course that focuses on double integrals, triple integrals, line integrals, and surface integrals. And so before we even kind of get started with the course, it's a good idea to go back and review some of the essential fundamentals that we're going to be using from Calculus 1, Calculus 2, and Calculus 3. Now, if you're on a semester system, this, of course, is going to be a blend of Calculus 1 and Calculus 2, but in the quarter system, it is Calc 1, 2, and 3. And so the first thing we have on our plate to kind of go over is kind of a very simple question, which is, what exactly is a derivative? Okay, and a lot of people might say, oh, it's an operation, it's a thing you do it to a function. Does it have to be a function? What does it represent? This is kind of what we're trying to get at. So what is a derivative? Well, a derivative, visually, this can be interpreted as slope, right? This, visually, this is the slope of a function, of a curve, maybe we'll say of a function, just to keep it simple, of a function at a particular point, right? At a particular point. And we introduced this topic in Calculus 1 because we realized that while we knew how to find the slope of straight lines, it's pretty easy. The slope of straight lines being y2 minus y1 over x2 minus x1, right? This is good old-fashioned rise over run. We said that this was insufficient if we had something curved, right? If we had something that was curved, we had some function f of x, and we wanted to figure out, what was the slope, say, at that particular point on our function, right? How steep was it? If you were going for a little walk up this hill, right? How steep would it be at that point? And it wasn't so cut and dry, and so we introduced this tool of the derivative. And so maybe a little more technically, the derivative basically represents, it's a comparison between how quickly the output of a function is changing relative to its input, okay? So the derivative, usually we use y and x for this, so I'm going to go ahead and do that. The derivative, kind of measures the change in y, or the change in our output, right? The change in y compared to the change in x, but not at a large scale level, right? We don't take a point here and a point here and look at the slope of the line between them. We don't do that. What we did in Calculus 1 is if we wanted to know the slope, say at this little green point right here, what we did was we decided to, use limits, and we picked another point that was somewhere over here, and we slid it really, really close to that one. And we said, oh, if you find the slope between those 2 points, right, if I move this yellow dot really, really close, and I kind of zoom in here, and I say, well, what's the slope of the line going between those 2 points? Well, it's pretty darn close to what the actual slope is at that green point. And so what this did is it introduced this tool, which we said when we're talking on a microscopic level, when we're saying, we're no longer taking 2 points and saying that the slope between them is, it's not dy, right? Or excuse me, it's not some delta y, some change in y compared to some change in x, right? It's no longer rise over run, right? This is the old school way of doing it. So we are not kids anymore. We are in Calculus 4, right? We know that on a microscopic level, when we shrink down that delta y and we shrink down that delta x, and we use limits, we get that the derivative essentially boils down to this, dy dx, right? This is a microscopic look at comparing a small change in the y direction and a small change in the x direction. Okay, so this is kind of what the derivative represents. So dx is a very small change, right? It's an infinitely small change. Infinitely small change in the x direction. And, ditto for the, dy. dy is, ditto. It's the same thing, but for the y direction. For the y direction. Okay. And so, the derivative operator, usually we would have some function f, and we might say, that you want to examine the change in something, right? Maybe I'll put a parenthesis here. The change in something with respect to x, and usually we would want to figure out the change in y with respect to x. Or if it was a function f, maybe we wanted to look at the change in f with respect to x. Or maybe we had a function and this function wasn't called f of x, maybe we called it bob. This is the function bob of x. And so if we wanted to examine the change in bob, compared to its input value x, we would do dbob dx, right? And this is how derivatives work and how the operator of the derivative works, okay? So hopefully that's a nice little reminder of just kind of, what it is we're doing, what this mystical, magical dy dx is, or on its own, right, what the dx is on its own. And we extended this concept into, in Calc 3, we talked about how, we don't have to talk about just dx's and dy's and stuff like that. We could also talk about, if we had, say, the curve of some function, we could talk about a small, like an infinitely small change in this curve, right? If this was a path C, we called this infinitely small change. You're gonna have to bear with me. I know you're like, oh, it's not infinitely small. We're gonna pretend that it's infinitely small. We called this infinitely small change in our curve ds. And we used this when we were calculating arc length. We said if I wanted to calculate, say, the total arc length from this point here to this point here, you would basically add up all of the little tiny ds's from the first point to the second point, right? So maybe we started at A, we ended at B, and we would get something like this. And this is where arc length stemmed from. And you're like, well, this doesn't look like anything I ever remembered. And that's okay, because remember, right, ds, we said, well, ds looks a little funky. I'm a little more comfortable with x's and y's. And so we went down to a microscopic level and said, well, if this is supposedly some infinitely small change in our arc length, right, it's really, 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 really tiny, that means that I can draw a little right triangle here whose components, whose legs are also infinitely small changes, right? And the idea is that we are so zoomed in at a microscopic level that we could very simply just use the Pythagorean theorem to say that ds was equal to the square root of dx squared plus dy squared. Now, we did things with this. We figured out how to calculate arc length. Hooray! We are going to use this again in this class. But for now, that's not really the point. The point is, just that these little d's, they mean, a very, very small, tiny amount of something, right? Okay. So that's how we use it. We have dx's, dy's, ds's. And then in Calculus 3, we extended into, we had full derivatives, and then we had these things called partial derivatives. So we introduced these things called partial derivatives. Okay, and we are going to need these in this class. Okay, so partial derivative. So what is a partial derivative? Well, the best way to think about it is if I have, make my little axis here. So my z-axis, my x-axis, my y-axis, and of course, label your graphs. That's a very good thing to do. Let's just pretend that I have a function that kind of looks like a mountain, right? So, I don't know, something like this. All right, cool. Whee. All right, there's my function, right? This is my 3D function, f of x, y. Great. And the idea was if I was somewhere on this mountain, right? If I was standing right there, right? If there I am, okay? Woohoo, right? I'm going on my little hike. And I wanted to know what the steepness was if I were to walk specifically in the X direction. That's not a very good color. Let's pick another one. If I were to walk in the X direction, exactly how steep would it be? And we introduced this operator. We introduced this partial derivative operator with respect to X. And we would apply this operator to our function f. So we would take the partial of f with respect to x, and then we would evaluate it at, whatever point that we were at. And the whole point was, just like the regular derivative gave us slope, the partial derivative gives us the slope going in a particular direction. So the partial derivative with respect to x, you can think of it as, the rate of change going in the x direction only. And so maybe as a quick example, maybe if we had a function, of two variables, maybe just x squared y, that if we took the partial derivative of this with respect to x, if we take the partial derivative of f with respect to x, we get 2xy. And, if this was a little confusing, remember that we get to treat y as a constant. We treat y as a constant. And this is kind of something that, can confuse people. Why do we get to treat y as a constant? Why do we just, treat it as a number? And the idea is actually very simple. At this point, that I'm standing on my mountain, right? Let's say it corresponds to this particular x and y value down here on the xy plane. Well, if I want to know the steepness going in the x direction, right? So see if I can make a better drawing than that. So I want to go in this direction exactly. Well, if I'm looking at the change in my function, so like df with respect to the change in x dx, is there any change in y happening when I'm looking at that rise over run? And the answer is clearly no, right? The y here is constant, right? When you pick a point, the y is constant. It never changes. So that is the reason why, oops, let me close this. That is the reason why when you do partial derivatives, you get to treat whatever variables that you're not taking the derivative with respect to, you get to treat them like constants, which is really nice. So partial derivatives, we also extended this concept. We had things like the gradient vector, right, which was essentially, that kind of was something you could calculate using partial derivatives, and it kind of pointed you in the direction you should go if you wanted to have the hardest climb up, right, the steepest change in your function, if you were to go walking in a particular direction. And we will talk more about the gradient vector again later in this class. But for now, just kind of giving a small refresher on derivatives and partial derivatives. Okay, we also had partial derivatives in the y direction. Very similar concept. We get to treat x as a constant. Hip, hip, hooray. And so the last thing that we really need to cover before we really dive into this class is, if we talk about derivatives, the very next thing that we should ask is what is an integral? Okay. And, people can very, very quickly say, oh, it's area under the curve. And I like to dissuade people from saying that because an integral really is not area under the curve. And let me kind of remind you where the integral as an operator came from in the first place. So the idea was that if we had a function, right, if we had some function f of x, right, going back to 2 dimensions, okay, and we had some range of x values that we wanted to integrate between, okay, that we wanted to figure out the area under this curve. And I know I just said the integral is not area, but sit tight with me for a second, okay? And I said, well, if I wanted to calculate the area under this curve, we used to use these things called Riemann sums, right? What we would do is we could cut up this cut up this interval into pieces. If we were using a right Riemann sum, we would use the right endpoints in each interval and create little rectangles like so. If we were using left Riemann sums, we would have done it using the left endpoints of each interval. And if we were using the midpoint formula, we would use the midpoint between each interval, and so on and so forth. And what we got were these rectangles, right? We got these little rectangles, and we said, hey, this kind of approximates the area under the curve. Kind of, but, if you zoom in here, clearly there are gaps, right? Clearly there is stuff that we are missing. It is not perfect, okay? And so the question was, how do we improve that? And originally, we used Riemann sums, and Riemann sums kind of look something like this. So for this particular example, a Riemann sum might look from 1 to 4 because there's 4 rectangles, and we would say, we need to calculate the height of each rectangle at any point, and the height of each rectangle was kind of given by the function evaluated at some x value. So maybe this would be like the first, if we were doing right Riemann sums, this would be x of 1, this would be like the second x value, right, the third x value, and this would be the fourth x value, and so on, right? And so we say, okay, well, if we want to calculate the area of this first rectangle, it's going to be the height, okay, times what? Times the width. And we say, well, how do you get the width? Oh, the width, well, that's not too bad. The width just came from, you took the distance between A and B. Oops, wish I could do math. You took the distance between A and B, and then you chopped it into, 4 pieces in our case, right? And so this gave us, right, this was the height, and this was the width. And this thing right here means you add up a certain number of whatever is here on the right side. In this case, we are adding up the areas of rectangles, because if we're talking about looking at a function that represents velocity, it's going to give you total distance. And if you're talking about looking at a probability density function, it's going to give you total probability, yada, yada, yada. So this thing was a super cool tool, but we said, hey, there's not enough rectangles here. We need it to be more accurate. And so just like with the derivatives, we put a limit in front of here, and we do this. And we replace this with the letter n. And you're like, where does this n come from? N just represents the number of rectangles that we would have. And so what is this saying? We say, well, as you let the number of rectangles that you have increase, right, go to infinity, we're going to get a better answer. And we said that this thing becomes the integral of f of x dx. Okay, so what does the integral represent? Well, let's see. In this case, the integral here is taking the place of this stuff here, right? It literally means, the integral means add up infinitely many tiny blanks, right? That is what the integral represents. Now, what are we adding up? Well, from calculus 2, we were adding up little tiny rectangles, right? Once we were done with the Riemann sums, and we graduated from doing Riemann sums, and I'm not going to redraw this entire thing, but I'll erase some of it, right? Once we were done with Riemann sums, and we were able to internalize the idea that we were going to have not just 4 x values to pick from, but that we were going to have infinitely many x values to pick from, we said, okay, well, at this x value here, I need to draw a rectangle. Okay, so we draw a little tiny infinitely skinny rectangle, and we had to ask ourselves, okay, well, what is the area of that rectangle? And I said, okay, well, if we're at a particular x value, that means that the height, right, the height is given by what? Well, the height is just given by the y value, by f of x. And you say, okay, well, that almost makes too much sense. This class I thought was supposed to be hard. And it's not, right? This is the height of a particular rectangle. And guess what the width of this little tiny, infinitely small, skinny rectangle is? Well, if you were paying attention to the part on derivatives, it is just dx, right? It is this really, really small, microscopic, infinitely tiny change in the x direction. And the analogy is, you can think about it as like it's a grain of sand, but when you add up enough grains of sand, you get a beach, right? You get the entire beach, you get all of the area under the curve, and in theory, in mathematical theory, it gives you the perfect area under the curve. Okay, so this is kind of the information that we're going to need to get started on the next section. So in the next video, we're going to kind of just hit the ground running. We're going to talk about how do we do this, not for a two-dimensional function, right? Because this is a 2D function. X goes in, right? And then y comes out. We have two variables, x and y. So this makes us a 2D function, and we know how to calculate the area under a 2D function. As I said, maybe I'll write some down. We talked about applications. The integral and the antiderivative process in general has a bunch of applications. We used to be able to calculate, total work. Right? Those terrible work problems from Calculus 2 where you had to haul buckets and ropes and pump out water and stuff. And you can calculate total work. You could calculate total probability, right? If this function represented, individual probabilities of things happening, then if you add up all those probabilities, you get the total probability, right? It almost makes too much sense. If we added up total velocity over some distance, over some time, right? So if we add up total velocity, right, over some total time. Well, if you're in physics, that gave us distance, right? Distance equals rate times time. And oops, I should not have this as a fraction, I suppose, because of what I just said, right? And the integral operator was, we would take the function, which is our velocity, and then multiplied it by dt, which was our time, and that should make sense because distance is rate times time, and that's why this integral would give us distance. So we had a whole bunch of applications of integrals, and we are going to revisit them for 3D functions in this class. So I think this about covers it. Everything that you're going to need to know, or that you should kind of be up to date with. You should also obviously be up to date with your algebra skills, things like that, because guess what? This entire class is based on algebra. And so yeah, that'll be it, and I'll see you guys in the next one.